is what we now call extensions of the field of rational numbers. Between rational numbers and real numbers, there are many fields. And such field is a quadratic extension of Q, that is of degree to extension. See, if you try consider a plus b root 2, where a and b are rational numbers. This is a vector space over Q of degree or dimension 2. So these are the next numbers that one likes to study. And these are very natural numbers because they appear in our study. For example, if one side of a right angle triangle is 1 and another side is also 1, then the diagonal, as we know by the Pythagoras theorem or Bodhayana theorem, the diagonal is root of 1 plus 1, that is root of 2. So this way, in practice, in geometry, you require these numbers which are square roots of some rational numbers. And therefore, these are studied. And can these numbers be added, subtracted, and get a number of the same form? Can you multiply these numbers? Can you divide one number by another? Such questions were studied. But you will be surprised to see that more complicated questions were also considered by Bhaskaracharya. So, maybe I will put off my video so that sometimes it is better. You will be able to see, hear the lecture in this case. So I will now start my presentation. And Bhaskaracharya had the idea of Shadvidha, means 6 operations. And what are these 6 operations? These 6 operations are addition, subtraction, multiplication, division, square. Can you consider square as a separate operation? Actually, square means multiplication of a number by itself. So nowadays we do not think that considering square is a good idea. But somehow Indian mathematicians thought that it is good to have a separate operation called square, because sometimes while finding product of numbers, if you use squares of some numbers, it is easy to do the calculation of product. And similarly, there is a corresponding operation, that is square root, which is required very often in calculations. So how to find the square root of a number which is a perfect square? And therefore Bhaskaracharya and previous mathematicians starting from Aryabhata have given methods of finding a square root and even a cube root. How to find the cube root of a number, that is also explained by Aryabhata and by later mathematicians. So let us see what Bhaskaracharya says in this Karani Shadvidha. Shadvidha, Karani means these surds, and sometimes the root of something, that is Karani. So 6 operations with surds that one wants to discuss. And a very interesting thing is there in Bhaskaracharya's method, that many times I will explain this thing. You require to factorize numbers in doing calculations with surds, especially finding square roots or even finding sum of 2 surds. Now this we never do in our usual school curriculum or college curriculum, but it is done by Bhaskaracharya, and by a very interesting method. So Karani Shadvidha, division is there. Addition, subtraction, multiplication, division, squaring, and finding square root. So division, we know, suppose I have a plus p root 2 divided by c plus d root 2. How do you rationalize the denominator? We know that you multiply the denominator by c minus d root 2. That is, we change the sign. We change the sign and multiply by that. And therefore, because you multiply the denominator, we also have to multiply numerator. And that is what we learn when we study division of two surds. This is what is explained by Bhaskara. But as we will see, more such things are explained which we do not include in our current curriculum. Okay. So this is one verse in Karana, Karani Shadvidha. Shadvidha means 6 operations. And what does Bhaskara say here? Because these numbers are new, so can you convert a positive number to a surd? Can you write 3 as square root of something? Yes, we do that. We know that. So 3 is equal to root of 9. We know that. But a negative number, can you write it as a surd? Now the problem here is, this is a difficult problem to start with. What people will do, as 3 equal to square root of 9. You should do it in the same way. Minus 2 equal to, what we should write? Square root of minus 2 square, isn't it? So it will be square root of 4. But then Bhaskara says that is not correct. You should write minus 2 as minus of square root of 4, not just square root of 4. So this is a very important starting point for surds. That the method that you use for positive numbers does not work for negative numbers. You should treat that separately. Because the meaning of, so square root, this operation square root has, when you write in this form nowadays, has only one meaning, that it is a positive square root. And this meaning is there whenever you are dealing with real numbers. Now complex numbers, there is a different thing nowadays. After that, complex numbers were discovered. And what is the positive complex number, negative complex number? There is no such concept. But for real numbers, we have this concept, and there we give unique meaning to square root of something. In mathematics, of course, later on, we give two possible meanings to square root. And because later on we deal with complex numbers or finite fields, as we go to higher studies, BSc, MSc, then we have to consider both the square roots like that. But the word Karani is used for a positive square root of a number. When you say root of 7, it has only one meaning. So if that meaning is what you have in mind, then you should write minus 2 as minus of root of 4 and not just square root of minus 2 square, because minus 2 square becomes plus 4. Okay. Similarly, opposite he says. So for kshajo bhave cha kshaya rupa vargaha. That's what he says. So if you, kshaya is actually negative. The word kshaya is used for negative. You should give minus sign to that. So kshaya number is minus 2, and its rupa means you take this magnitude, that is 2, and take the varga of that. So then square root of that you should take. So minus 2 equal to minus of root of 4. That's what you should do. So chet sadhate aso karani tuva heto. If you want to write using karani, then you should give minus sign, and you should consider Kshaya number, its rupo means its value, and then take the square of that. That should be used, and this sign and this square root. तथा च ऋणात्मिकायाः तथा करण्याः. Suppose minus 49 is a karane. Karane means there is some square root sign. But if it is runatmaka, means does it, if it have minus sign, runa sign or minus sign, then तथा करण्याः मूलम क्षयः रूप विधान हेतोः. So for this thing, you should take moolam, you take the square root, and then you should take kshaya of that, means minus of that. So that is what the meaning of this verse is, and he tells you how to deal with negative numbers and karani, means square root sign under the radical sign. Okay. Now, this is also another interesting thing. As I have told you, if you want to simplify a surd, usually in our high school curriculum, we simplify only surds of the type let me write down here. Uh, 2 plus 3 divided by 7 minus 5 backslash 3. You see, you consider numbers of this type in which only one square root of 3, right? Only root of 3. You do not have numerator root 5 and denominator root 7, for example. Or you do not, this is in the high school, we do not solve difficult problems of this type. But Bhaskaracharya is not afraid of difficult problems, and he actually tells you in this two verses, Dhanarva Vyatyayam. Vyatyaya means change the sign. Dhana Runa. Dhana becomes Runa, Runa becomes Dhana. So you interchange the signs. Ipshitayaha Chede Karanya. Chede in the denominator, Karanya in Asakrut Vidhaya. Asakrut means do it many times. Tadruk Chida Bhajya Haro Nihanya. Multiply numerator and denominator by changing one sign. And then you go on doing like this, and ultimately you stop when there is only one karani left. Eka eva yavat karani hare syat. Hare means in the denominator. Eka eva, only one karani means square root sign is there. Up to that you go on doing like this. So let me just explain this by means of an example. Suppose you want to do this simplification of 1 upon 1 plus root 2 minus 2 root 3 plus root 5. And you want to get rid of the denominator. And so rationalize the denominator. Then what you will do? That is the question. And this question we never solve in our high school curriculum. We only solve problems of the first type, 2 plus root 3 upon 7 minus 5 root 3. You multiply numerator and denominator by 7 plus 5 root 3. By changing the sign, minus becomes plus. That is what Bhaskaracharya has mentioned, that Dhanaruna, Dhanarnata Vyatyayam. Dhanaruna Vyatyayam means interchange. That in the denominator. So here what does Bhaskaracharya say? There are 3 karanis here, 3 square root signs. What you should do? First of all, you try to get rid of this root 2. How? Change the sign of root 2. Plus becomes minus. So 1 minus root 2. And the rest you keep as it is. Don't change sign everywhere. change sign here only. Now you multiply numerator and denominator. Okay. After you simplify this, root 2 will disappear. But there will be root 3, root 5, and root of 15 will also be there. Root 3 into root 5 is root 15. That may also be there. Let us see if it is there or not. You check that. But even then, you don't worry about that. You go ahead after this simplification and you change the sign of another surd. Maybe root 3. Whatever coefficient of root 3 is there, if it is positive, make it negative. If it is negative, make it positive. Multiply by something else that kind of conjugate with respect to root 3 only, not with others. And then you multiply numerator and denominator, and you go on doing like this till only one surd is left. Only one Karni is left. Maybe it is root 15 left out. You see, although root 2, root 3 into root 5 is root 15, you don't get additional surds there. Because even if you multiply root 3 by root 15, what happens? Root 3 into root 15 is 3 times root 5. So again, only root 5 is appearing there. That means no new surds essentially appear there. So this is how Vascular explains how to simplify the denominator of a very complicated expression like this, which we do not do in the high school curriculum. Okay, so you see that still Vascaracharya's Bijganit has new things which we have never discussed in the curriculum. Okay. Now this is a new thing, addition of two surds. How do you add two surds? So let us take this problem. How will you simplify root 23 plus root of 207? Now you may think about it in the following form. 207, try to factorize it. So can you factorize 207? In this case, yes, it is divisible by 3 because 207 is divisible by 3. So again divisible by 3. So it is 23 into 9. Now square root of 9 is 3, you take out. And then 3 times square root of 23 is the answer. That is the simplification. And then you say it is 4 times root 23. That is how you can do the problem. But Bhaskaracharya does not explain it this way. The reason can be given in the context of the current times. Here you have factorized 207 and you said it is 9 into 23. But suppose these are very large numbers and instead of 3 square into this number 23, there are very large numbers. Now how will you proceed? Because factorization can be very difficult. So Bhaskaracharya says in that case, he gives a method to deal with such things. He says root 23 plus root 207 is equal to the square root of 23 plus 207 plus 2 times square root of 23 into 207. So Vascaracharya says that 23 into 207 is 4761. This is a perfect square and its square root is 69. And if you want to really simplify this, it is required that the product of these two quantities is a perfect square. That's required. Otherwise, you can write it in this form, but there is no simplification. The expression will look complicated only. if it is not a perfect square. Okay, so here 4761 is a perfect square and its square root is 69. So our answer is root 23 plus root 207 is equal to root of 23 plus 207 plus 2 into 69 is equal to root of 368. He has written it in the form square root of something, Karani. So your answer 4 times root 23. Already he has taken that 4 inside and multiplied by 16 and got the answer 368 square root. And what Bhaskaracharya uses here, very simple idea that a number is the square root of its square. Now this is why a you are writing as in a complicated way as square root of the square of a. That is exactly what is useful here, and you will see in this method of Bhaskaracharya, this 23 plus root of 207, this quantity is written, you see, is equal to this number is written as square root of its square. And now you see, you expand this and you get exactly what was written there. Square of 23 is this. Square of root of 207 is here. And then 2 times the square root of 23 into 207. And that is actually 69. We see that 23 into 207 is 4761 is a perfect square and its square root is this. See, finding a square root is simpler than finding finding factors. And Bhaskaracharya and Aryabhatta also in the 5th century, they have given methods of finding square roots. So that's why they say square root are basic operations. They are used in doing other operations. So this is a very brilliant idea of Bhaskaracharya in that it avoids factorization, and so it is preferable in modern times as factorization of large numbers is considered difficult. Now you see very interestingly this is amenable to generalizations. For example, suppose you want to simplify root of 3 plus 4i plus root of 3 minus 4i. You want to simplify this. Now you don't know the square root of 3 plus 4i. Of course, you can do it by using polar form, etc. But still, if you use Bhaskaracharya's method, you can do it. What Bhaskaracharya says, this is equal to, so first of all, the product of these two numbers, is it a perfect square? Let us see. So 3 plus 4i into 3 minus 4i. If you consider that, uh, product of these two numbers under the radical sign you should consider, and that should be a perfect square. Yes, this is 3 square plus 4 square is 5 square. It is a perfect square and its square root is 5. Of course, even if it comes out to be 7, suppose, then it is a perfect square in the sense that its square root we know in our domain. So that is root 7. So anyway, square root is 5. The numbers are taken for convenience to illustrate. Now, what is your answer? Answer is square root of 6 plus 2 into 5. So the answer is 4. 6 plus 10 is 16. So the answer is 4. Because our method tells us here that the given numbers 23 plus 207 in this case plus 2 times square root of that. Similarly here, uh, 3 plus 4i plus 3 minus 4i plus 2 times uh, that 5 that we obtained. So answer is 4. So root of 3 plus 4i plus root of 3 minus 4i comes out to be equal to 4 actually. That is the simplification. Now there are various questions. What is the meaning of square root of 3 plus 4i? Because there are two square roots and because these are complex numbers, you cannot say that it is positive, it is negative. So what you should do? So because there are two possibilities for root of 3 plus 4i and two possibilities for root of 3 minus 4i also. So there are four possible answers because we don't know. You cannot say this is what the square root in my mind. We cannot say that. So you observe that there are four answers and we have obtained only one answer, right? So root of 6 plus 2 root 5, I can immediately say the other answer is minus 4. So there are two answers now which we have obtained for this, although we expect four answers. But what you can do is, when you do this operation, square root of 3 plus 4i plus 3 minus 4i and plus 2 times root of the product. Product is 5. So root of that product is 5. So this root of 25 is obtained as plus 5, but it can be minus 5 also. So the other possibility is root of 6 minus 2 into 5 or root of minus 4, that is 2i or minus 2i. So there are four possibilities. And all the four possibilities can be obtained by the method of Vascular. So this Vascular method, although he gives for usual integers, it can be used for such expressions for complex numbers also. So we have four possible answers. And the answer is obtained without actually finding the square roots of 3 plus 4i and 3 minus 4i. Usual method would be find two square roots of 3 plus 4i, find two square roots of 3 minus 4i, and then pair them properly to get four answers. I hope you have understood this method of Vascular, how you can combine two surds, and this addition is possible when the product of these two numbers is a square. Now, in this example, root of minus 4 is there. Is minus 4 a square? Now you will say, Vascular says minus 4 is not a square because square is positive. But we know we are dealing with complex numbers, so minus 4 is a square and it is a square of 2i or minus 2i. So we write that and you can get it. So similarly, 25 was there, and we have two square roots, and second square root we have used -5, and then we have gone ahead. So this something is a square or not, it is to be seen in the system of numbers that we are dealing with. So I am giving an example of a finite field also, because nowadays in the MSc level or even in BSc level, you study finite fields because these are very much useful in computer science. So let us look at Z13. It is the field with 13 elements, 0, 1, etc. up to 12. Addition and multiplication is modulo 13. Now, how will you solve root 2 plus root 5? How will you simplify this sum? Can you write it as root of some number? This root 2 plus root 5, can you write as square root of something in the finite field Z13? Now, first of all, the problem here is you cannot find a square root of 2 in this finite field. In this finite field, there is no square root of 2 available. You can check that. You just find the squares of 0, 1, 2, etc. and 12. You will see that no square is equal to 2. Similarly, no square is equal to 5. Now, what is the suggestion of Bhaskaracharya? Bhaskaracharya says you can simplify, provided 2 into 5 is a square. Product of the two numbers is a square. So 10 should be a square. Now the question is 10 a square? Now usually such questions are dealt with using Legendre symbol. So those who know Legendre symbol can understand the calculations. Otherwise, you can just take it from me that 10 is a square. The third method is you actually square various numbers and you will see 10 is available there. But anyway, especially when you deal with large numbers, you first decide whether that number is a square or not. So 10 by 13, because 13 is 1 mod 4, you can write it as 10 means -3. So it is -3 by 13, Legendre symbol. Now -3 is -1 multiplied by 3. So because of homomorphism property, this is -1 by 13, Legendre symbol, into 3 by 13. Now -1 by 13 is +1 as we know, because 13 is 1 mod 4, so -1 by 13 is +1. Okay. Now this 3 by 13, because 13 is 1 mod 4, you can invert 3 by 13 and get 13 by 3. Now 13 is numerator, go modulo 3. If you go modulo 3, you will get 1. So 13 by 3 is 1 by 3. And 1 is a square, so Legendre symbol 1 by 3 is equal to 1. So 10 by 13 Legendre symbol is 1. That means 10 is a square modulo 13. So again, don't mind if you do not know Legendre symbol, because the answer comes out to be 1. Usually the answer is 1 or -1. If it is 1, it is a square. If it is -1, non-square. So here 10 is a square. And in fact, we can check that the square root is 6. 6 square is 36. And 36 is 10 modulo 13, because 2 into 13 is 26. 26 plus 10 is 36. So 10 is a square and it is a square of 6. Okay. So now we can go ahead. We wanted to find out root 2 plus root 5 you can want to combine. So the answer by Vascular method is square root of 2 plus 5, that is 7, and plus 2 root 10. So root 10 is 6. So 7 plus 2 into 6 is again 12 plus. So you are going modulo 13. So answer is 6. Okay, because 12 is -1, 7 minus 1 is 6. So answer is root of 6. The other square root answer is minus root of 6. And if you want really 4 answers, because this is root 2 plus root 7, in the finite field, there are two possible values of root 2 and two possible values of root 5. They are not lying, the square roots are not lying in Z13 itself. They are lying in a bigger field, but we want to simplify it. Okay, so root of 13 is minus 6 also. If you use that, then 7 minus 2 into 6 is minus 5, that is 8. So root 8 is 2 root 2 or minus 2 root 2. This gives four possible answers. So here, two answers were 5 and so we got root 2 plus root 5 is equal to either root 6 or it is minus root 6 or it is in the finite field. The two values are either root 8 and minus root 8, or you can write 2 root 2 and minus 2 root 2. This way, you can give the four answers. Other fields also, this method works. And otherwise, if the Vascular has not suggested this, we had no clue of how to simplify root 2 plus root 5 in a finite field. Okay. Now, another thing is finding square roots. And let us try to find the square root of this third 29 plus 2 root 210. So the problem here is usually in the high school method, we do this problem by trial method. Find the square root of 29 plus 2 root 210. So the idea is usually like this. You expect a square root which we can write as think of this as a possible square root. So if this is a square root, then the square of this root a plus root b is this. Okay. Now if your square is actually a plus b plus 2 times ab. Okay. So this is what you expect. A plus b plus 2 root ab. That means this a, you try to write 29 as a plus b and try to write ab as 210. Okay. Find two factors of 210 whose sum is 29. Now 210 has many factors and you should do some adjustment, try, and ultimately you will succeed in doing it. But Vascular does not say this way because you have to factor 210. Now, if that happens to be product of two large primes, then it will be very difficult to factorize it. So Vascular does not say that you factorize that number and find such factors whose sum is equal to that 29. He doesn't say that. So what he says, actually 210 is 15 into 14 and 229 is 15 plus 14. So answer is root 15 plus root 14. That is the square root. But for large numbers, factorization can be difficult. And so we may have to try many possibilities. On the contrary, Bhaskaracarya gives a root finding algorithm for a square quadratic surd a plus root b based on the methods that he has already introduced. Okay, so how does Bhaskaracarya solve this problem? Suppose you want to solve this problem square root of 5 plus 2 root 6. Factorize 6 so that the sum of the factors is 5. That's what we do usually. But Bhaskaracharya says, of course, here the answer is 3 into 2 is 6, 3 plus 2 is 5, so answer is root 3 plus root 2. It's very simple here because the numbers are small. What Bhaskaracharya does is, he says, first of all, you write it as a plus root b. That means that 2 you put inside 5 plus root 24. Now what we do, 5 square minus 24. A plus root b, a square minus b. That is his method. 5 square minus 24 is 1. Okay. This is a perfect square. This is a requirement. Is a perfect square. This is required. If it is not a perfect square, then you will not get a simplification. You will get answer. But that is not a simplification. It is just an answer. If you get that this number is a perfect square, you get a nice answer. Now what you do? Find the square root of this number, that is 1. Then 5, this is this a plus root b. So a, 5 plus 1 by 2 and 5 minus 1 by 2, that is 3 and 2. This is the answer of Bhaskaracharya. So Bhaskaracharya says 5 square minus 24, that should be square. Then find its square root. Find its square root. If you take minus 1 as also, then no problem, because 5 minus 1 by 2 and 5 plus 1 by 2. So you will get same numbers in the different order. 2 and 3 you will get. So even if you find the negative square root, no problem, please note. And now once you obtain root 3 plus root 2 as one square root, the other is obviously minus of that, so you don't have to say that. Similarly, 29 plus 2 root 210. First write it as 29 plus root 840. Now 29 square is equal to 841. So we have 841 minus 840 is 1. Right? A square minus b. The square of this minus this. So 841 minus 840 is 1, which is a perfect square with square root equal to 1. Then 29 plus 1 by 2 and 29 minus 1 by 2. That is the answer. So 15 and 4. So we get root 15 plus root of 4. Okay. So we have got the same answer which was obtained by trial method. Again, if you want to solve this for general field situation, there what you require is a square minus b should be a perfect square in that field. Now, very interestingly, we can take a plus ib. Is it a surd? Can you think of a complex number a plus ib as a surd? Certainly yes, because our field is real numbers. So this is generalized sense. Field is rational numbers and you are adjoining root 2. Similarly, filled with real numbers, and you can adjoin I, which is square root of minus 1. So this is also a surd over real numbers, a plus ib, because of that I equal to square root of minus 1. So we want to find the square root of a complex number. How will you do it? How will you find the square root of a plus ib? So write it by Vascular method. You can find the square root of a complex number. Write a plus ib as a plus root of minus b square, isn't it? Because that I you should take inside. That means you get multiply by minus 1. As minus b square is not a perfect square, this is a surd expression over the field of real numbers. Now, to find the square root of this, what we should do? A square minus of minus b square. That means a square plus b square. This should be a perfect square over real numbers. So answer this question, is a square plus b square a perfect square over real numbers? Answer is yes. Why it is a square over real numbers? Sum of two squares may not be a square. That's what we think. But here, it is a non-negative quantity. A square plus b square is a non-negative quantity, and any non-negative quantity is a square in the field of real number. It has a square root, whatever it is. So its square root is root of a square plus b square. So what is the answer? By Vascular method, the answer is a plus root of a square plus b square divided by 2, and a minus the root of a square plus b square divided by 2. These are the two square roots. This is the sum of these two. You see here, let us take here plus root 15 plus root 14. Okay, once you get these two, then take the sum of them. So here, similarly, what do you do? Take the sum of these two quantities. So the sum of the square roots of these expressions is the answer. Is it a real number? This sum? No, you see that this is a positive quantity, and this is a negative quantity. So root of this plus root of this first expression, like root 15, remember, plus root of 14 means root of this quantity. But this is a negative quantity. So in that square root, I will appear there. Okay, I will appear. So that the square root of a plus ib is given by root of a plus root of a square plus b square divided by 2 plus root of this quantity a minus root a square plus b square divided by 2, and this is a negative number, so its root will have I times something. So this is how the Bhaskaracharya's method works even for finding roots of complex numbers. Now Bhaskaracharya goes ahead and he asks such a question: find the square root of 10 plus root 8 plus root 56 plus root 60. And Bhaskaracharya has one verse which says that you can go ahead also. So maybe let me describe how you, because now that not much time is left, we can stop here also if you have any questions. Otherwise, I will explain this. So what Bhaskaracharya says is, just as a square minus b, in this problem you find out a square minus b minus c. 100 minus 8 minus 56, which is a perfect square, 36. Now you consider 10 plus 6 by 2. 6 is square root of this. And 10 minus 6 by 2, that is 8 into these two numbers we have obtained. Out of these two numbers, 2 is kept as separately and 8 is used for further analysis. Okay. Now this root 60 was not used in this process, root 60. And this 8 we have obtained, which want to use for further analysis. So consider 8 plus root 60. This is going to be a perfect square of a third expression. It is going to be, means you are sure that it is going to be. If the original number third expression is a perfect square, then this is going to be a perfect square. And you see that 8 square minus 60 is Vascular method we are using here. 8 square minus 60, a square minus b, it is going to be 4. 4 is a perfect square with square root 2. 8 plus 2 by 2, same method. 8 minus 2 by 2 is gives 5 and 3. So Vascular method, this gives root 5 plus root 3 as a part of the answer. And the final answer is obtained using previous root 2. Thus the square root is root 5 plus root 3 plus root 2. Now here what will happen? So we have obtained the square root, and if you square this, you do not get the previous answer. I explained the method. So the point is that the method works provided it is a perfect square. Already it should be a perfect square. So sometimes you may arrive at a wrong answer. So we have to check whether it is working or not. Okay. Method works if we start with a perfect third square. But Vascular has given the method and it works. So I have told you this thing, and now let us look at this. Root 3 plus root 5 plus root 7 square is 15 plus root 60 plus root 140 plus root 84. This is perfect square we know already. So now this here it will come out. I will in 1 minute. 1 minute is left for me. So what you will do? Take 15 and this thing you take. Take two surds together. 15 square is 225. Subtract these two, you get 25. Square root is 5. Okay. Now 15 plus 5 upon 2 is 10, and 15 minus 5 upon 2 is 5. Go ahead with 10. Go ahead with 10 and 5 you keep separately. Then left out is 84, remaining third here 84. Consider 10 plus root 84. Now 10 square minus 84 is 16, square root is 4. 10 plus 4 by 2 is 7, and 10 minus 4 by 2 is 3. Final answer is root 5 plus root 7 plus root 3. Now you can do similarly 4 things together. Also, you square it and then what happens? So maybe Bhaskar has said that you can extend this and you can solve such problems. So anyway, we stop here. I have told you these two methods of combining two surds. This is not done usually in our usual curriculum. And also how to find square root of a surd. And square root of a surd can be obtained easily if it is of the form a plus root b, but it can also be found if it is a plus root b plus root c plus root d. And Bhaskar has given a verse in which he says, if there are 3 square roots, it can be obtained if it is a perfect square. There can be 6 surds, there can be 10 surds, square root signs, then it can be obtained. So his method works is what Bhaskar says. So this is very interesting, and it is not done in our school curriculum because of the nature of the difficulty of this problem. But Bhaskar has given methods to solve such problems, and you see we have noticed that whatever he says for usual numbers, integers, it is also true for complex numbers, and that is very interesting that this method is amenable to generalization. So With this, I stop my talk, and if you have any questions, we can uh, discuss those. Or if you have any comments to make, that also you are most welcome. Yeah.
Uh, Professor Sriram is here. Sir, would you like to comment anything? Please, sir. Please unmute, sir.
Sorry, yeah. I know that Professor Katre has been working on this area for quite some time. It's quite refreshing, again. I would like to have your slides, sir. That's quite interesting,
Yeah, okay,
Yeah,
I'll send. Yes, right. Yes.
yeah.
Okay. These things, because Bhaskaracha has said it is only one verse, but one
Yeah,
requires to explain it more. So I have
yeah,
also,
exactly.
because what happens is, what are the conditions under which you guarantee that this process will work and so on. Such questions are
Yes,
there.
yes.
And Bhaskaracha says that, yes, I had told you how to start, now you work out. So he asked
Correct,
you to
correct.
go ahead. That is the problem.
That's right. Yeah,
Yeah, but initial step itself is interesting, and this way it will work. That he has explained is very important. Yeah,
yeah.
yeah, okay.
He's quite teasing at times,
Ah, yeah,
He's playful and teasing, He will
yeah,
leave something for
yeah, yes, right.
the readers. Yeah,
He also explains in one verse that
yeah, exactly.
he should not explain too much. That's what he says.
Yes, that's right. That's
Because
correct. Very good.
yeah, some things should be worked out
Yeah,
by the those who are
yeah.
listening to that. Yeah.
That's right.
Okay.
Any other questions or comments from our audience? Madam Smita is there, I think. Madam, would you like to draw any comment? I think she is not. So
Not
if there
really.
are, yes, yes, please. Madam, please.
No, I don't think I have any questions on
Yeah,
this.
yeah. Okay, madam.
Yeah,
So, sir, please share your slides so that it can be shared with the participants.
yeah.
So, thank you very much for your talks. You have covered mainly three topics: Kutakka method, failed equations, and search beautifully. And you have uh, draw attention to some important works done by Bhaskaracharya and Brahmagupta and some more things. So, as you mentioned, these topics are such that these are usually not covered in our syllabi, and they are not part of curriculum. So, I think participants certainly we will see these matters and materials from books and try to learn something about our old golden legacy, I can say, from Indian mathematicians, which was ignored for some time, and now people are doing a lot of work on this one. So thank you once again, sir, for your support also, and I hope you will be also in the other lectures also.
Yes, I will try. Yes, thank
Yeah.
you. Yeah.
Yeah.
So we will have, I think, 15-minute break, or you can say 10-minute break. Please join to 3:45 because the next lecture will be at 3:50 by Professor Venkateswara Pai from Aisher, Pune. So please join on time. Okay.
Okay.
Good afternoon, sir. Sir, namaskar. नमस्कार सर. Okay. Sir, next lecture will be at 3:50. Dr. Venkateswara Pai will deliver his talk. So just we have a 10-minute break.
Yeah, that's what I expected.
Hello.
I'm sorry I could not attend in the morning because I had my classes and then there was a colloquium.
Oh, okay, sir. No problem. Your presence is enough at this time. So we have 10-minute break. Dr. Pai will deliver his talk at 3:50. He has already joined.
विराम केलाय तो काय त्याच्या प्लेटमध्ये होती पटकन गार होईल काय प्लेटमध्ये होईल मी गार होईल
आज जाना पड़ा
आलं का माझं? आहे चालत